It's not the only vector. There are other vectors, such as Darwin, if you have some papers about it. So this is the one we practically carry these pieces on board the ship and delivers them somewhere else quite nice and fresh. There are a lot of criteria which has been suggested and decided, and none of the guidelines and none of the things which has been put together discusses this matter in a way that addresses all the issues and all the challenges. This is not the IMO job to do, I have to say. IMO is not there to tell us how to run the marine transportation system. IMO is there to protect certain things, same as class society, the same as the port state authority. But each one of them has a certain job to do, and so does the ship owner and the ship operator. But whether there are contradictions within the regulations, that there are multiple problems which are associated with one element of this problem to the others, we need to see. This is what we are going to see, how this will affect the design of the system. In anything we want to do, if you want to design a shipyard, if you want to design a system, if you want to design a system, we are somewhere that we want to start. We understand the requirements for the need. This is what we call an engineering design. It is not relevant to the ships. It's relevant to any engineering system we want to put together. The next step is to organizational structure, how the things are going to connect to each other, who's going to talk to whom, and which engineers we try to put together. And then we look at the markets and targets, who are going to be the end users, who are going to buy my system, who's going to sell my system, who's going to operate my system, how much benefit I'm going to get. Then we create solutions. Some of the solutions have USP, because unique selling points, whether the ship built in Bangladesh have a unique selling point, which they are the cheapest, or they are the best, or they are the greenest. So these are the things you do, and then you go to evaluation, to technical assessments, different assessments, multiple criteria analysis, and then you send it to classification, whether it gets approved or not, to enter the market. And once it is entered to the market and you start making money, or you originally close your company. That is what happens, and obviously all of this has to happen in a time scale which is appropriate for delivery. Why Korea became Korea? Because they reduced this timeline from there to a much shorter time. They have something yesterday. This is what engineering design looks like for anything we want to do, whether it's a large system or a small system. Internally, within your organizational system manufacturing unit, you get the order, then you put together the technology group, and then they start looking into the mission profile of the ship and the design and sustainability of that particular design. Then you put the generic design, and then you look into verification plans, and then you put the specific and relevant regulations next to it, whether it comes from IMO, from ISO, or any other standards. Then you do the first round of design assessment and optimization, and then the peer review. You do the final design and dissemination of the design to the system. This is what happens inside a small design unit in a company. As far as ship design and ship system design are concerned, we can do it at 3 different levels. We can do it as a retrofit, if the system is going to go on board the ship. You can do it during the build, and you can design something which you can sell it off the shelf, because it can be supply. And whatever you do with these 3, which you want to deliver a system to be manufactured for the application of the ships, on board the ships, you have to go through either of these routes. And to be able to do that, you have to take a lot of things into account. Whether this system you want to make, it has VOC associated to it, corrosion, leakage, emissions, ballast water, all the issues associated with the damage to the environment, damage to the ship, damage to the safety. Okay, this was all the things that we do as engineers, and then we take into account all these parameters. These are all the internal structures that we put together to be able to put the system together, or ship together, or we can retrofit it, or we can build it. Put everything all together, looks like this. It requires funds, the ship, the system, or whatever it is, comes from the bottom, goes through the system, and then the end user and the classifier and the authorities are going to become your design, purchase it, approve it, or disapprove it, or allow you to enter the jurisdiction of the water, or to be used in that particular state. This is the whole thing. But is this enough? Is this because if you are a part of this system, as I said, you can easily get isolated to one aspect of delivering that particular system. The whole question comes, question of sustainability, and this word has been used all over the place. I didn't put the word sustainable in the title of the presentation, because there are so many different definitions of sustainability that would have deterred you from being even interested in this lecture. The word sustainable has been used and abused. If you go to dictionaries, if you go to the United Nations website, the word sustainable has been defined by different people. If you talk to the people who are involved in the food, they say sustainability is only about food for the people. So they talk about the green parties, they only talk about emissions and the clean air and water. So to them, sustainability means what makes them sustainable. You talk to the ship owners, they say, I should be sustainable. Have enough money to pay the salaries of the engineers who are working for them. So the word sustainable, I said, probably is the most abused word ever in English, and particularly in our particular discipline. In Newcastle, we have put together a group, and then we looked into, can we define sustainability in, first of all, in a way that it is applicable to different parts of engineering and different parts of science and different parts of society and different parts of government and government structure. We came up with three things. That a sustainable thing, whatever it is, must be enough, must be for all, must be forever. And the whole target of sustainability is that it has to make us good ancestors. This means that future generation are not going to hate us, and they're not going to swear at us. As if those people who lived 10 years, 20 years, 200 years before us, they don't ruin the earth. Again, we are in the danger of putting this next to the food. The food must be enough, the food must be for all, and food must be forever. No. We would like to translate this to anything you want to do, even to yourself when you wake up in the morning. Am I sustainable today? Is the car I'm driving sustainable? Is the food I'm eating sustainable? Is the technology I'm using sustainable? And I want to define this, let's say, about the ballast water management system. A ballast water management system must be designed to be good enough to treat the water at the flow rate, at the size of the ship, at the emission profile which is required by that one. It must be designed good enough to meet IMO criteria, Classification Society criteria, and many other technological criteria. It must be strong enough to withstand the damage on board the ship. It must be powerful enough to take the flow rate of that particular ship. So we can see the word enough comes only in the spec of the ballast water management system. For all, it must be with all the sea waters around the world. The best ballast water management system is the one which can be fit on board all the ships. It could be operated by all marine engineers. It could be sold and repaired by all shipyards and installed by all shipyards. This is the target. Whether we can achieve it or not, we don't know. And it should be forever. Forever doesn't mean it should last 200 years. The ship doesn't last 200 years. But the definition of forever means it should not pollute the environment more than the amount of environmental protection it wants to offer. It should not pass the environmental problem from one corner to the other one. This means it should not deal with the issues which we are not unaware of yet, in a way that is going to damage the environment. And also, it must be sustainable on board that particular ship in a way that it should not either outlive or be short-lived compared to the life of the ship. So each one of these could be defined quite specifically for a ballast water management system. And of course, if you treat your ballast water, it's going to make you a good ancestor, because you're going to keep the fish for the future generation to be able to eat fish and chips if they want to, or to eat the nice fish that we had last night. So So if this is the target design, it's a holistic view, if I translate the enough for all forever for a ballast water management system, and in a more general way, an engineering system, if this is the target I would like to achieve, first of all I have to meet IMO's guidelines. In this particular case it's called G2 and G8 and G9. I don't want to go to the details because there is a paper this afternoon I'll explain what they are. But these are the IMO governing lines about design of this system. Then the next one comes. Is it installable? Can I install it easily on board ships? Is it producible? Can this be produced around the world?